Okay, YouTube, this video is going to concern itself with the fundamental trig identities and what they are and how we can use them to simplify a lot of the time trigonometric expressions. So this is sort of a preamble to my next videos in which we will simplify trigonometric expressions, but we're going to familiarize ourselves with these identities in the first place. So let's go ahead and start with an identity. An identity in its simplest form here, I can give an example of an identity. This would be an example of an identity, and the reason why it is an identity is because either side of this equation, no matter what you substitute in for this input or this variable here, you're going to get a true statement. So for instance, if I said, well then let x equal 2, we'd have 2 times 2 plus 3 times 2 would be equal to 5 times 2. And of course it is the case that 4 plus 6 indeed equals 10. So we say that identities are beneficial to us, or they're to our benefit to use, because in other words we could say 2x plus 3x could be rewritten as 5x, and essentially what we could do is we could say, since these are the same thing anyways, we could substitute 5x wherever we see something like a 2x plus 3x. Well, our fundamental trig identities, I'm going to try to breeze through these as quickly as I can, but we want to familiarize ourselves with them so we can make some simple trig substitutions. So starting with our reciprocal identities, these are probably the most basic, but they essentially say this. We say the sine of an angle is the same thing as the 1 over the cosecant of that angle. That is, that they are reciprocals of one another, and vice versa. We could say that whenever we see a cosecant, we can really rewrite this as 1 over the sine of that angle, and they mean the same thing. So often we find that we don't write sines as 1 over cosecants, but we do often write cosecants as 1 over sines. So what I'm going to do is I'm basically going to list out the three popular reciprocal trig functions here, and we're going to say that they can be rewritten in this form. So whenever you see a secant, you can rewrite it as 1 over cosecant, or cosine, pardon me, and then we say whenever you see a cotangent, we can rewrite this as a 1 over tangent. 1 over tangent. So our basic reciprocal identities say that we can rewrite our reciprocal trig functions as 1 over the original trig functions there and express them that way. Okay. As far as our quotient identities go, these ones are pretty prevalent. We see them quite often, but we say that the tangent of an angle is the same thing as if we took the sine of that same angle over the cosine value of that same angle. So whenever we see a tangent, we can replace it with the sine over cosine, and vice versa. Since we know that cotangent is the reciprocal of tangent, we could say then this would be the same thing as cosine over sine. Okay, so these replacements or substitutions we use quite often as well. So now we get down to the Pythagorean identities, and I would say that more than any of these identities that we talk about up here or over here, the Pythagorean ones are the ones we tend to concern ourselves with quite a bit. So you're going to see me write the most basic Pythagorean identity, and that is that sine squared of an angle plus the cosine squared of an angle always comes out to equal 1, and this is very much true. What we're going to do is we're going to memorize just this one Pythagorean identity, because with this one we can build all of the other different formats of this identity. So starting with this, if we have sine squared plus cosine squared equals 1, how can we get our secant, cosecant, tangent, cotangent Pythagorean identities? Here's what we're going to do. We are going to say, what if we were to take this entire expression and divide it through by, say, sine squared? Okay, this is how we'll build our first one here. So I'll actually show the work on this one. I'll get this blue out of the way. Sine squared of an angle plus the cosine squared of an angle, of course, equals 1. But I'm begging the question here, or making the argument that what if we were to go through and divide everything by sine squared? What this allows us to do is build one of our other three Pythagorean identities, and what we see here is essentially this. We get sine squared over sine squared. This gives us a 1. And then we say cosine over sine. Now what we know about cosine over sine is this. According to our quotient identities or ratio identities, cosine over sine is cotangent. So if we were to have cosine squared over sine squared like we do have here, this is essentially going to be a cotangent, but a cotangent squared. So we say 1 plus cotangent squared equals now 1 over sine squared. And again, 1 over sine, what we know about 1 over sine is it's this identity up here. So we could replace that 1 over sine with really a cosecant. And since this is a 1 over sine squared, this really should be written as a cosecant squared of theta. So this is the second of our three Pythagorean identities. Okay. And in order to build the third one, what we would have done is we would have gone back through here, and instead of dividing everything through by sine squared, we could divide everything through by a cosine squared. And you can see how we can manipulate this into its third Pythagorean form. But essentially sine squared over cosine squared, well, sine over cosine is tangent. So this would come out to be a tangent squared of theta plus now cosine squared over cosine squared would be 1. And this would be equal to 1 over cosine squared, and that is the reciprocal of cosine. That would be a secant. So 1 over cosine squared would be a secant squared. So we often use these identities to rewrite their forms and make replacements or substitutions. Okay, so while I'm talking about these three Pythagorean identities down here that we want to have in our back pockets all the time, what we're going to do is we're going to twist this top identity around quite a few ways. So the alternate forms, I'm going to write the alt forms of the basic trig identity here, or sorry, Pythagorean identity, is going to be this. What if we were to take the cosine squared and drop it on the right side? What this means is whenever we see a sine squared of theta, we know that if this original statement is true, then the sine squared of theta would be the same thing as 1 minus the cosine squared of theta. Okay, so what this allows us to do is make replacements. Whenever I see a 1 minus cosine squared, I can replace it with just a sine squared, or wherever I see a sine squared, I can replace it with a 1 minus cosine squared. As a follow-up, what I want to do also is this. I want to make the note that whenever you see a 1 minus cosine squared, as we have here, we could rewrite that as a difference of squares. As a matter of fact, let me make this a little bit wider. As a matter of fact, we say that this is a difference of two squares, where 1 would go on the front of each of these binomials, and we say that the cosine of the angle would go on the back of these two binomials, and we would say that these would have to be conjugate pairs, so 1 plus, 1 minus. So again, whenever we see a 1 minus cosine squared, we could rewrite it as a 1 plus cosine, 1 minus cosine, which comes in handy quite a bit of the time. And then our third way to split this apart here, or second way to split it apart, pardon me, for our alternate form is this. What if we were to take the sine squared and subtract it over to the right side? This also means that cosine squared of theta would be equal to 1 minus the sine squared of this angle. Okay. So we'd say 1 minus sine squared is the same thing as a cosine squared. They're replaceable, interchangeable, as well as we could say, well then cosine squared also would be this difference of squares where we have 1 plus the sine of theta and 1 minus the sine of theta, where these are conjugate pairs. And so all of these down here in our Pythagorean land here were built off of this main primary identity, and then we could just use them interchangeably. Okay. So as far as our cofunction identities, we just need to remember that the sine of an angle theta will always be the same as its cofunction of its complement, or the cofunction of its complement would be written as the cosine, since it's its cofunction, and then the complementary angle would be just 90 degrees minus the original angle, theta. That would be the complement of this original angle, or you could say pi halves minus theta. So this is also true with our cosine here. We'd say, well then the cosine of an angle must be the same thing as the sine of its complement, so this would be true also. So whenever we see a sine, sine of something pi halves minus an angle, we could just replace that with a cosine. And this is very true with secants and cosecants, because we know about two things being equal, then their reciprocals are also equal. And we could say that the cosecant of an angle would be equal to the secant of pi halves minus the original angle, or the complement of that angle. And then also this, we could say that the tangent of an angle is equal to the cotangent of pi halves minus the original angle here. Or in other words, tangent is equal to its cofunction of its complementary angle. Okay, and I will let the audience fill in these other two over here. Basically, you could switch the relationship around between these two things to get this one over here, and these two things to get this one over here. And so last but not least, we say even and odd identities. It is just very useful to know that cosine is the only even function. So I'm going to list it thusly. In terms of our even function, we say cosine is an even function, and essentially when you take the cosine of a negative angle, what we could do instead is say that it has to be the same thing as the cosine of positive that angle. So in other words, whenever you take the cosine of a negative thing, you can just replace it with the cosine of that positive thing. It's a really neat substitution. And so what this means is that it's also true that it's reciprocal, secant, when you plug a negative angle into it. Since it is an even function, we can just make its angle positive. As far as all the rest of the odds go, we could say that all of the rest of the trig functions are odd. So for instance here, sine is odd, and when we plug a negative into it, we can just go ahead and place that negative out front. Okay, so again, it just means that if you take the sine of a negative, we can stash the negative out front, and this is also true for its reciprocal. So the cosecant of a negative angle is the same as the negative cosecant of positive that angle, and then these are also going to be true for tangent. So tangent of a negative angle is equal to negative tangent of a positive that angle. And if we were to be taking the cotangent, its reciprocal of a negative angle, it's also an odd function, so we can just throw that negative out front. But using these basic identities, what we're going to do in my next video is just come back to this page, essentially, and put these to work for us by using simple substitutions and simplify some trigonometric expressions that are complex and made simpler. Cheers.